Hi everyone, my name is Justin Cross and this is my submission for my Transport1 Homework 6. The problem statement states that we want to compute the time-varying temperature profile of a 50-meter bar via finite difference with a step size of 1 meter and our diffusivity alpha as 1 meter squared per second. There's a lot of steps to that, this first one being we want to show that this equation here satisfies the uniaxial time-dependent heat diffusion equation with no heat generation. Now that is a mouthful to say, so it's actually a pretty easy equation. I'll write it up here. So it is the partial derivative of the temperature with respect to time equals our diffusivity alpha times the second partial derivative of temperature, with respect to x. Just like that. Now what we want to show is that this equation for a temperature satisfies this equation. And the way we're going to do that is we're going to calculate these partial derivatives, plug them back into the equation, and if it satisfies that equation, those sides should be equal. So let's go ahead and do that. So we have the partial derivative with respect to time, just like that. And if we take a look at our equation, we have two parts to it. One is time dependent and one is position dependent. So when we take a partial derivative, with what we're taking it respect to will be differentiated, while the other part will not. It'll just stay the same. So in this case, because we're differentiating with respect to time, we're going to take the derivative of the time-dependent part, while the position-dependent part does not change. So this becomes negative alpha k squared e to the negative alpha k squared t times the position-dependent part, which is e to the I k x. Just like that. Now we want to find the other partial derivative here. So the second partial derivative of the temperature with respect to the position. And the same idea applies where the time-dependent part will not change. So that's e to the negative alpha k squared t multiplied by the second derivative of the position-dependent part. So that'll be I squared k squared e to the I k x. Just like that. Now what is I? We know that I is the square root of -1. It's our imaginary number. So if we take the square of it, we just get -1. So what I'm going to do is I'm going to replace this I squared with a negative sign because it equals -1. Now let's plug these two partial derivatives back into the original equation. I'm going to do that up here. So the partial of temperature with respect to time, we have negative alpha k squared e to the negative alpha k squared t e to the I k x. And what does that equal? That equals alpha, which is a part of the equation here, multiplied by this partial derivative. So that is negative k squared e to the negative alpha k squared t e to the I k x. Just like that. Now with a little bit of rearranging, we can see that both sides actually equal the same thing. They both equal negative alpha k squared e to the negative alpha k squared t e to the I k x. Now, because both sides equal the same thing, we can say with confidence that this original equation for a temperature satisfies our heat diffusion equation. All right, so part 2 of this question tells us to derive the forward differentiating scheme to determine our temperature profile. And I also wrote below it our heat diffusion equation. Now, before we start this question, I want to show some of the nomenclature. And with that, I'm going to show a little illustration here. So let's pretend that this is our bar and it extends on both sides like that. We're just looking at a little piece of it. And these are all of our little parts of the bar. How are we going to communicate our temperatures at each part of the bar? So let's take this part right here, for example. This part has a temperature, right? But what does that temperature depend on? It depends on both the position at the bar and the time since we started looking at this. So because of that, we're going to need two scripts. We're going to have a j and an n, where our j is our position script and our n is our time script. So to better show this, say we want to look at this bar 1 over from the bar we originally looked at. That bar is going to have a temperature at j plus 1 and n, just like that. And the same idea goes for the bar behind it. It has a temperature of j minus 1 and n, just like that. Now let's say we keep looking at this bar, but we go one time step further into the future. That would mean our n value goes plus 1 for all of these, just like that. So that is how we're going to describe our temperatures as we go and derive this forward differentiating scheme. So let's get rid of our illustration here, as good as it was. And let's start deriving this scheme. So how are we going to do that? What we're going to do is we're going to take this heat diffusion equation and rewrite it in a way that we can take into Google Collaboratory and show how this temperature changes with both position and time. So let's do that. So let's take our change in temperature with respect to time. What is our derivative? Well, it's a little bit of change in a temperature over a little bit of change in a time. And that's pretty easy to do with our nomenclature here. So it's going to be a temperature, and it's going to be subtracted from another temperature, right? That's the definition of a change. And then over delta T, just like that. Now, what are our scripts going to be? Because only the time is changing, our position script is not going to change. So that is a J and a J, just like that. Now, if we want the change in time, like we're looking at, that'll be an n plus 1 and an n, because they're right next to each other in terms of time, and subtracting them is going to be a small change in time. And we can apply the same idea to our second derivative. We're going to take a little baby step and start with the first derivative of x. Now the same idea applies. We've got a temperature minus a temperature over delta x, just like that. Now again, our time, because our x is changing, our time is not, our n's are going to stay the same, but our x's, our j's, are going to change. So a j plus 1 and a j, just like that. And we can take this idea and apply it to a second derivative here. So if we get second derivative of temperature with respect to x, it's going to be a little bit of change in this over a little bit of change in x. So that'll be tj plus 1 n minus tjn all over delta x minus the tjn minus t of j minus 1 of n over delta x all over delta x, just like that. Now that we have both of our partial derivatives, we can plug these back into the equation, and let's see what we get. So we've got our partial with respect to time. I'll rewrite that here. So tjn plus 1 minus tjn all over delta t equals, the next part of our equation is our alpha. So alpha times this second derivative. So that's tj plus 1 n minus tjn over delta x minus tjn minus t of j minus 1 n over delta x all over delta x, just like that. Now what we want to do next is try and separate our temperature that has a different time variable. So everything here has a time of n, except for this first part here, it has a time of n plus 1. So let's separate that and put everything else on the other side of the equal sign. So we get a temperature of j and n plus 1 is going to equal, we move this to the other side, so tj of n plus, we got an alpha delta t over delta x squared multiplied by, we simplify this top row here, we have a temperature at J plus 1 and N minus 2T at J and N, and then plus the temperature at J minus 1 and N. Just like that. Now finally what we're going to do is we're going to define, so it up here, our value R, and we'll say that equals alpha delta T over delta X squared. Just like that. So, because we just defined that, I'm going to go ahead and replace this whole value here with R. Just like that. Now that's actually going to make it a little easier for us when we go into Google Collaboratory and code this out, because that is the next step. What we want to do is take this equation that we just found right here, box that off here. Oh, not you though. There we go. We're going to take that equation, we're going to put it into Google Collaboratory, and we're going to graph out the temperature profile and see how it changes with respect to both position and time.
All right, so here we are in Google Collaboratory. What I've done is I've taken the problem statement and I've copied and pasted it up here. And I've also taken the equation that we got in part 2. I've written it down and I took a photo of it, and we have that photo right here. And we're going to refer back to this for a little bit. So, what do we want to do? We probably want to start with our imports. So we're going to use numpy and we're going to make a plot. So we'll use plotly dot make subplots. So import numpy as np and from plotly dot subplots import make subplots. Make subplots. And see if it runs. Perfect. All right, what else do we want to do? Well, what do we know? We know alpha, so alpha. We have our dx value. We're going to have an nx value. I'll get to that in a moment. And we also have a time dependency, so I'm going to do the same thing, a dt and an nt. And we also have a value for r, and we'll define that as well. So what was alpha? We show up here. Our thermal diffusivity is 1 meter squared per second. I'll plug that in. We have a step size of 1 meter. That's our dx value. It's a 50 meter bar, and if we're going with a step size of 1 meter, then we're going to have 50 segments. So 50. And then dt and nt are our time-dependent ideas. So dt is the step in time that we're going to take. We'll say 0.1. And our nt is how many steps we're going to take. With respect to time, we'll say 2,000. And then our value for r, we defined that already. That's alpha times dt divided by dx squared. Perfect. Now, what do we want to do next? We probably want to make a list of all the temperatures within our bar. So let's do that. So we're going to call that t. We'll say numpy dot full. And our shape, how many segments are we going to have? We're going to have nx segments. And the fill value, we'll say that starts at 25 degrees Celsius. Just like that. And then if we look at our temperature, it's just an array with 25. And we look at the shape, it is 50 long. Perfect. Now, let's say when we look at this bar, we're actually heating it up on both sides. So what are we heating them up to? That's up to us. So we'll say at the front end of the bar, we heat it up to say 150 degrees Celsius. And then at the back of the bar, so T of -1 being the last unit, we'll say we're heating it up to 80 degrees Celsius. Now if we look at our temperatures again, we can see that's exactly what happened. We have at the front 150 and at the back 80. So we probably want to graph that here just to show what our initial temperatures look like. So let's make a figure. So make subplots. How many rows? Rows, just one. We're just wanting one graph. And then columns, same thing. 1. And then figure dot add scatter. It's going to have an x value, it's going to have a y value, and it's going to have a name. The name is initial, just like that, and our y is going to be our temperatures. And we should probably make another list for our x values. So we'll say x is numpy.a range of nx times dx, just like that, and we'll say that is our x value. Perfect. And there we go. So we can see for our initial graph at the front of the bar, it starts at 150, goes all the way down to 25 until the end of the bar where it goes up to 80. Perfect. Now what's next? Well, we want to simulate this equation, right? So let's start doing that. So our temperatures, let's see, so our temperatures from 1 to -1, I'm going to say that equals that same idea, the temperature from 1 to -1, and then plus our R value times, let's see, so it's a temperature in front minus 2 times the temperature there plus the temperature behind. So that should be pretty easy to do. So the temperature in front is from 2 to the end minus 2 times the temperature from 1 to -1, and then plus the temperature behind. So that'll be from 0 to -2. There we go. Now if we take a moment and look at what that just did, we can see the temperatures right next to where we're heating the bar up are changing just a little bit. Now what we want to do is simulate that nt times for each time step we're going. So we do for I in range 1 to nt and tab this over. What does that look like as we go through? It looks like this. This is what our temperature profile is, just in a number array format. So what we want to do is take these values as we go through and iterate through the times and display them on our graph. But we don't want to display all of them. We probably want to display once every 100 time increments. So we'll use modulo for that. So if I modulo 100 equals 0, then we want to add it to the scatter plot. So I'm just going to copy and paste this and rename it. Instead of initial, it's going to be I. And then at the very end, we want to show the figure. So fig.show. And what do we see? We see that as the time goes on, the temperatures get closer and closer to a straight line between the top and the back of the bar. So to better show that, I'm just going to add a little more time because we weren't fully at that straight line. So if we run that again, we'll finally see that, yeah, it's basically a straight line if we go far enough into the time. Now what I want to illustrate after this is a little problem that we have with this equation in itself. And it has to do with the value of R. So what we want to do is change this value of R a little bit. And by doing that, I'm going to change the value of alpha. So if we change the value of alpha to 5, and we run this again, it seems okay. There's nothing fishy that's wrong with this. But if we change this to say 5.01, what do we see? We see something that does not resemble a temperature profile. What we see is a little bit of instability. Now, why is that? That's what this next part of the video is going to talk about.
So what we saw in part 3 showed that our original equation here had a little bit of instability when we changed the value of R. Now what we want to do for part 4 is to apply our von Neumann stability analysis and show the constraints for our stability. So what I've done here is I've written our original equation up top here, and I've also written the temperature equation that we solved for in part 1 that we showed fits our original heat diffusion equation. So what I want to do next I want to just remind us that our t's, our j's, and our n's are both counters for our position and our time. So what I'm going to say is that our x value is going to equal j delta x, and our t value is going to equal n delta t. Now the reason I do that is so we can rewrite this equation here. So our temperature, we'll say, is equal to E to the negative alpha k squared. And instead of t, we're going to use n delta t. So n delta t times E to the I k, and instead of x, we're going to use j delta x. J delta x. And you'll see why pretty soon. But next, what we're going to do, I'm going to take this top part here, and I'm going to factor out a tj of n from this part in the parentheses. And you'll see how we're going to do that by using this solved equation. So if we do tj n plus 1 equals tj of n plus r tj of n, what does that leave us? What does that leave us in the parentheses here? That leaves us with an e to the I k delta x minus 2 minus e, no, my bad, plus e, there you go, to the negative I k delta x. Now how does that work? What we did here was we factored out a temperature at a specific position and a specific time. Now when we did that, all three of these temperatures here are at the same time. So we took out the time-dependent part of the temperature completely. We also took out the position-dependent part of the temperature at J. So when we did that, that left us with a +1, a J plus 1 turns into this time-dependent position, but without the J. And the same idea applies here. Instead of a J, we had a J minus 1. So that left us with a position-dependent part of the solution here. Now what we want to do next is we have values of e raised to a power here. What we're going to use is Euler's identity to further expand what we have in those parentheses. So what we know is e to the ix equals cosine of x plus I sine of x. Just like that. That is by definition, Euler found that out, and now it's widely used. So we're going to rewrite our equation here in terms of those cosines and sines. So if we go tjn plus 1 is going to equal tjn plus rtjn, what does that leave us in the inside? Well, we have a cosine of k delta x plus I sine of k delta x delta, oops, there we go, perfect, k delta x minus 2 plus e to the k, oh, my bad. I don't know where I was going with that. It's not an e, it's a cosine. So a cosine of k delta x minus I sine of k delta x, just like that. I finally get to break out my red marker here because this right here and this right here actually cancel out, just like that. So let's keep going here. Let's further factor out a few things. Let's rewrite this first. So we have a tj n plus 1 equals tj of n plus r, not a big R, a little r, plus r tj of n. What's inside here? We have a 2 cosine of k delta x minus 2, just like that. Okay, let's factor out a 2 here. So I'll just make it easy on ourselves. Let's do something like that. We have a 2r tjn cosine of k delta x minus 1, just like that. And then finally, let's factor out a tj of n. And I'm actually going to rewrite this one here. So tj of n is going to equal, oh, this is plus 1, tj of n 1 plus 2r cosine of k delta x minus 1, just like that. Now, if we take a look at what we've just found out, what we have in this parentheses, we cannot let go over 1 or under -1. If that happens, we're going to get compound interest on our temperatures as time goes. So for example, if this equals 2, our Tj of n will equal 2. That means the next time it'll be 4, and the time after that it'll be 8, 16, 32, so on and so forth. And we can't let that happen. So what I'm going to do, I'm actually going to get rid of some of this stuff here, and I am going to rewrite this equation up top. So let's do that. We've got a T, J, and N plus 1 equals temperature at J and N, 1 plus 2R, right? And then multiplied by cosine of K delta X minus 1. Just like that. All right. So as I said, we cannot let this inside parentheses value be greater than 1 or less than -1. So let's set up an inequality here. So we'll say -1 is less than this value, 1 plus 2r cosine of k delta x minus 1, and that can't be, just like that. All right. So let's get our eraser here, make it a little easy on ourselves. We subtract 1 from both sides. We get -1 minus 1 is a -2, and this is a 0. Just like that. Let me get rid of that plus sign a little more. And now let's take a look at what's inside this parentheses here. So what values of our cosine, or what values can a cosine be? They can be between -1 and 1. And if we want to maximize what's inside of this equation, make it the largest magnitude, let's say if it's a -1, we get a -1 minus 1, we get -2, which is a pretty big value in terms of magnitude. While if it's +1, this becomes 0, and this is actually, it wouldn't fit, but it would be pretty close in between the inequalities. So if we say the minimum value of this cosine has to be -1, -1 minus 1, just like that, we'll get a -2 in these parentheses. So let's rewrite this inequality. So -2 is less than 2r, and then inside the parentheses we'll have a -2 is less than 0. Just like that. All right, what's next? We want to find the value of r that's going to make our equation unstable. So if we keep going with this, we actually see that r has to be less than 1/2. Just like that. I skipped a few steps. We're not showing all the algebra. Just trust me on this. R has to be less than 1/2. And we actually saw that in our inside Google Collaboratory. When our value of R went over 1/2, we got all those squiggly lines on our graph showing the instability. So this is the constraints of our original equation. Now what we want to do is find a separate equation that doesn't have this constraints that we can go into Google Collaboratory and we can fiddle around with. We can plug it in, and we can show our time varying temperature profile of our bar without the need to worry about our constraints. So our next attempt to make a finite differentiating scheme is going to revolve around the Crank-Nicholson approach. We haven't used that yet. We used a different approach before. The difference between what we're about to do and what we did before, this is what we did before. We had our values in our parentheses. We had one value that was at a different time. We had our R value. I actually undefined our R value here. We'll redefine it in a moment. And what that led to was instability in our value for R. It couldn't be over 1/2. So what we want to do is find a new differentiating scheme and prove it has no stability constraints. Now how we're going to do that, I just said, we're going to use the Crank-Nicholson approach. And the difference between that and what we used before is within this parentheses. Instead of using this in our parentheses, we're going to take the average of these values between two different times. So what I'm actually going to do here is I'm going to add on to this equation. And plus, and we're going to have these three values just at a different time. So I'm going to rewrite them here. So tj plus 1 n minus 2 tj n plus tj minus 1 and n. Just like that. But instead of at the time n, it's going to be at the time n plus 1. Just like that. And then again, it's the average. And we're going to divide all of that by 2. Just like that. Now we're actually, I just drew that. We don't really need that there because we're going to move it over to this part here. So this will be plus 2 delta x squared. Just like that. And then once again, we're going to define this new value as r. So we'll say r equals alpha delta t over 2 delta x squared. Just like that. And like that, we can replace this value here with r. Beautiful. Now the same approach as we took when we were differentiating this original equation, we want to get all the values that have an n plus 1 on one side and all the values that don't have an n plus 1 on the other. So how are we going to do that? Well, let's start. So we're going to have, let's see, a negative r times t j plus 1 n plus 1, and then let's see. Well, we've got minus 2 tj of n there, and plus 1. So what is that going to be? Well, let's see. So plus tj of n plus 1 plus 2r, r tj and n plus 1. We can actually factor that here pretty easily. So that'll be plus 1 plus 2r, tj and n plus 1, and then what? We get a j minus 1 here. Perfect. So it'll be a minus r t of j minus 1 and n plus 1. Just like that. So that's the left side that has all the n plus 1 values for the temperatures. And that's going to equal, let's see, we've got, so what did we just do? We factored out all of these n plus 1 values. I'm going to take my red marker and cross them out. Just like that. Let's see. Now on the right side, we've got an r, t, j plus 1, and n. And then let's see, we got a plus 1 minus 2r, t, j, and n. And then plus r, t, j minus 1, and n. Just like that. So what we've done is we've taken this equation up top and we have separated it in between the two values for our times. We've got all the temperatures with n plus 1 time on one side and all the temperatures with n time on the other. And this is actually the equation that we are going to use when going back into Google Collaboratory and graphing out our temperature profile. But what we want to do here is we also want to prove that it has no stability constraints. And we're going to use the same approach that we did last time when we were showing the stability constraints for the original equation. So what we're going to do is we are going to factor out a t, j, and n plus 1 from the left side here. And we're going to factor out a t, j, and n from the right side, just like that. Now, what is that going to leave us with on the inside? Let's see. We got a negative r. Let's see, we took out a j, so it leaves us with a plus 1. So that'll be an e to the I k delta x, and then plus 1 plus 2r, and then minus r e to the negative I k delta x. That's what we have on our left side, and the same idea applies on the right side. So let's see. Oh, okay, plus 1 there. There we go. So it leaves us with an r e to the I k delta x plus 1 minus 2r plus r e to the negative I k delta x. Just like that. Now if we keep going and we reference back to when we were doing this before, we had something like this where we had an ik delta x and a negative ik delta x, and the sign values that had the imaginary number attached to it canceled out. So if we keep going with that, let's see, we got a t, j, n plus 1. What do we have here? Well, we have a 1 plus 2r, and then minus 2. It'll be a cosine of k delta x, I believe, just like that. And that equals a t, j, and n. Same idea. We have a 1 minus 2r, and then plus 2 cosine of k delta x. Just like that. And then if we move this value over to the other side, we're going to separate our n plus 1 values from our n values. We get t, j, and n plus 1 is going to equal t, j, and n multiplied by, we have a 1 minus 2r plus 2 cosine of k delta x all over 1 plus 2r. Is that right? Yeah, I think so. Minus 2 cosine of k delta x. Just like that. And the same idea as before, this value here has to be between -1 and 1 in order for no stability to happen as our time increases. So I'm going to clear the board a little bit. I'm going to move this up to the top, and we'll come back and we will show how this has no stability constraints. All right, so we're back. We have this equation up top, and we're going to prove that this fraction right here will never be greater than 1 or less than -1. So the first thing I'm going to do, I'm going to take this and I'm going to rearrange it a little bit. So we're going to have a 1 minus 2r times 1 minus cosine of k delta x over 1 plus 2r times 1 minus cosine of k delta x, just like that. And the reason that I did this is to prove, well, we'll see that 1 minus cosine of k delta x will always be greater than 0, just like that. Let's say greater than or equal to, just like that. Because, as we proved earlier, the cosine of k delta x will only be between -1 and 1. And if we want it to ever try and be greater than 0, it needs to be, well, it needs to do something that it's unable to do. Because this value is only between -1 and 1, and the 1 minus anything between that will always be greater than 0. So I'm going to define 1 minus k delta x as, we'll call that y. And we're going to say y is always greater than 0, just like that. So if we rewrite this, so we've got a 1 minus 2ry over 1 plus 2ry, just like that. And again, if we look at our r value, let's rewrite our r value. So r equals alpha delta t over 2 delta x squared. R will also always be greater than 0. So we can define another variable, like a dummy variable here. So we'll call it z. Z is going to equal 2ry. And z will also be greater than 0 at all times. So that leaves us with this fraction 1 minus z over 1 plus z. Now, for all z is greater than 0, right? Now, for all values z is greater than 0, there is no way that this value will ever go out of bounds between -1 and 1. So let's pick, for example, let's say z is equal like 3 or something. This is going to leave us with 1 minus 3 over 1 plus 3, or 2/4, or 1/2. 1/2. 1/2. And 1/2 falls in between the values of -1 and 1. And we'll try it again. We'll say, how about 13? 13, 1 minus 13 over 1 plus 13. That leaves us with 1 minus 13 is -12. You know what? That was a -1/2. I accidentally did that wrong. And the 1 plus 13 is 14. -12 over 14 is -6/7, which also falls in between -1 and 1. Because of this property of what's inside our fraction here, we can say that our value here that we derived from our Crank-Nicolson finite differentiating scheme has no stability constraints as opposed to what we did beforehand, and therefore our R value can be anything we want. What we're going to do is we're going to take that original equation that we derived, the Crank-Nicolson equation, and bring it into Collaboratory, and we're going to use it to solve and show our temperature profile with no stability constraints. So for the final part of this question, what we want to do is implement our Crank-Nicolson scheme into Google Collaboratory and graph the temperatures as a function of time. This isn't Google Collaboratory, however. Before we go there, I want to show how we're going to solve this. So what we're going to do, what we have here first off, is our Crank-Nicolson finite differentiating scheme. And what I want to do is explain this a little further before we get into Google Collaboratory. And how I'm going to do that is with an example. So what I'm going to do is I'm going to draw a bar here. This bar is going to have 6 parts. So let's see. A little middle part, and then 1 and 2, and 1 and 2. There we go. So it's not perfect, but it's going to work for our example. And these are parts. Let's say this is 0, 1, 2, 3, 4, and 5. Just like that. Now at each part here, each part has a temperature, and that temperature is described by the time at which it was looked at and the position at which it is in. Now how are we going to explain all of those temperatures for all of those positions at the times n+1 and at the time n as 1? Well, we're going to use matrices. So let's draw out our matrices here. So trying to make this as organized as possible. We have one big matrix here multiplied by a vector, and that's going to equal the right-hand side of the equation. So how are we going to fill this in? Well, let's start with looking at our equation up top here and looking specifically at the J values. When we're looking at our J values, we're going +1, for example, here, and -1, for example, here. And because of that, we need to look both forward and backwards at our positions when we are defining what we want to look at on the bar. Now, if you take a look here, for 5 here, for position 5, there is no position 5 + 1, or 6. So we're going to have to account for that. And the same idea for position 0. There is no position 0 - 1. There is no position -1. And that leaves us with these 4 values inside at positions 1, 2, 3, and 4. What we want to do is have our matrix equation here reflect what we have written up at the top. So down our vertical column here, we're going to have our temperature at 1 and n+1, and then T2 at n+1, T3 at n+1, and T4 at n+1. Just like that. And what does our matrix here represent? Well, this matrix is going to represent the constants attached to each value when we're looking at all of these equations. So this is best understood if I show you an example. So let's do that. Let's say we're going to show the example for position 3. So what we're going to do is we're going to replace all of the J's here with 3's because that's the position we're looking at. So let's do that. I'm going to write that down here. I'm sorry if I'm in the way. I'll show you once I'm done. So negative r t 3 n plus 1 plus 1 plus 2r t, you know what? 4, there we go. 3 n plus 1 minus r t 2 n plus 1 is going to equal r t 3 at n plus 1 minus 2r. Again, I did it again. That's 4 t 3 at n plus r t 2 at n. Just like that. So what I have done is I've replaced all the j values here with 3's. So for example, this first value here, it becomes a negative r times t. J plus 1 is 3 plus 1, which is 4, and then n plus 1. And then all the way through, that's exactly what I've done. So how does this relate to what we're doing within the matrices? Well, we have columns here. We're going to have 4 columns. Let's see if I can write those out here pretty quick. 1, 2, 3, and then 4 rows relating to each j value. So what we did was just for the temperature when j equals 3. And then these constants refer to each, these columns refer to each constant when writing out that equation. So for j equals 1, did we have anything that had a temperature when this bottom value equals j? Well, when this bottom value equals 1? No, we didn't. So that means that value on the matrix is going to be 0. Did we have one for when it was 2? Yes, we did. So that became a negative r. And then when it was 3, it's 1 plus 2r, 1 plus 2r. And then when it's 4, it's back to negative r. Just like that. And then the right side of the equation we just put over here as our other vector. So that is going to be an r t for n plus 1 minus 2r t 3n plus r t 2n. Just like that. So that is one row of our equation here. So if we keep going with this idea, say we do this for 2. Well, that would be a negative r here, a 1 plus 2r here, a negative r here, and a 0 here. And then the same idea applies. So r t 3 of n plus 1 minus 2r t 2 of n plus r t 1 of n. Just like that. And then finally, the same idea applies for the temperatures at positions 1 and 4. So this becomes a 1 plus 2r, negative r, 0, and 0, and then a 0, 0, negative r, and 1 plus 2r. I'm going to get rid of these column lines to just make the matrix a little easier to see. Just like that. Perfect. And then the same idea applies here. So this is going to be an r t 5 of n plus 1 minus 2r t 4 of n plus r t 2 of n. And this is an r t 2 of n plus 1 minus 2r t 1 of n plus r t 0 of n. Now remember when we couldn't go further to the right at position 5 or further left at position 0? We need to account for that because, for example, in this top row, well, if we had a row above, we wouldn't have been able to put this part of the equation in. So to make up for that, we need to do a plus an extra r t0 of n here, and then the same idea applies for the bottom, plus an r t 5 of n. Just like that. Now, if we take a look at this matrix here, we notice that here we have these vertical or these diagonal bands of the same values, right? Just like that. Now, this is actually called a sparse matrix, and a banded sparse matrix because we have these diagonal bands going across the matrix. And we actually have specialized ways of solving for these matrices and solving for equations such as the one we have here. And we're going to use that specialized way of solving for matrices within Collaboratory. And by doing so, we are going to significantly cut down the amount of work that we have to do. So instead of solving this within Collaboratory row by row or column by column, we can just use the solve banded function that we're going to implement and make finally our temperature profile for our bar using our finite differences with our step size and our diffusivity. And finally, we will be able to see how the temperature changes with position and time.
So here we are back again in Collaboratory. What we have here was what we tried to do in Collaboratory beforehand, and we saw that it ended up giving us a whole bunch of instability as the value of R went above 1/2. But thankfully, with the new Crank-Nicholson approach that we're going to use here, we've shown that it has no instability. Therefore, no matter what the value of R is, we are able to solve for the temperature profile. So that's what we're going to do here in Collaboratory this time. So thankfully, a good portion of this that we did beforehand was just set up for the problem. So it's actually, we can reuse it. So I'm going to copy and paste that and put it down here. I'm going to rechange the value of alpha back to 1. And we redefined our value of R, so I'm going to add the 2 in the denominator there. I'm also going to make these figure 2, just so we have those two figures separated. And what do we see here? We see the same thing that we saw beforehand, where our first temperature value was 150, our last was 80, and from anywhere else it was just 25. Now we said at the end of the last part that we were going to use something called a banded solving equation within Python. So let's take a look at what that looks like here. Now what is it asking us to do? So what we're doing is our value for an A, our matrix for A is our banded matrix. As we can see here, it has a couple bands. So a band of 1, a band going from 5 to 1, and then 2s, and then negative 1s. And then the value of B is the one-dimensional array that is on the other side of the equation. So if we take a look at our equation and see if we can relate this to what we're trying to do. Well, this matrix here that has our 3 bands is going to be our values for A, and then our B on the other side of the equation is going to be this right-hand side. So what we want to do is we want to take these values for A and B and we want to put that into the self-banded equation, and it should spit out a new temperature profile for us. So how are we going to set up this value for A? Well, let's see what they did here. So the value for A that they are plugging into their self-banded equation is AB here. Now let's take a look at what that is. Well, from visual looks, it looks like it's just taking a band and taking it from going diagonal to horizontal. That's exactly what they did. So these values for negative 1 went here, these values for 2 went into the second row, and then the 5, 4, 3, 2, 1 went into the third row, and the 1s went into the fourth row. So that's pretty easy. Then we can do that here in Collaboratory. So let's make our A. Let's take a look. So np.zeros, zeros just to start. How many bands did we have? We have 3 bands. But then how long is it going to be? Let's take a look here. Well, in this example, we had 1, 2, 3, 4 columns in this array. But we had 1, 2, 3, 4, 5, 6 different values for our nx. So I think it's safe to say that this is it's going to be nx minus 2 columns long. All right, so let's plug that in, and let's take a look at what A looks like. Yeah, so as we can see, it is 3 rows. We got 1, 2, 3 rows of nx minus 2 columns long. Perfect. Now, what do we want to fill those zeros in with? Well, we want to fill them in with the values of this matrix. So let's say the first band is -r, the second band is 1 plus 2r, and the third band is also -r. So that should be pretty easy to do. So A, we want the first row, so 0, 0 comma, and then equals -r. Let's see if that works here for us. So -r, and then look at A again. Perfect. So that first row is now all the values for -r. And then we can do the same thing for the first value, or for the second row, the first, the index of 1, so 1 comma all of those, equals, it was 1 plus 2 times r. And then for the last band, for the second index, it was also -r. So if we take a look now, that's exactly what we have here. So our value for -r, and then our 1 plus 2r, and then -r. Perfect. All right, what's next? We probably want to set up the one-dimensional array for b as well. So b is going to equal np dot zeros. Again, it's going to be nx minus 2 long. And if we take a look, that's exactly what it should look like. Awesome. Now, how did we set up this right-hand side of the equation? Well, it looks like, oh, we got it up here. It's r times the temperature in front plus 1 minus 2r times the temperature plus r times the temperature behind. So that should be pretty easy to do. So b equals going to be r times the temperature in front. What is that? That is 2 to the end plus, let's see, 1 minus 2 times r times the temperature from 1 to -1, and then plus r times the temperature behind. So that is, it'll be from 0 to -2. Awesome. Oh, let's fix that here. All right, so if we shift enter and take a look at our values for b, perfect. So that's what we want to see. So we started off with the values for 25 at the temperatures, and this is just a little change that we had to do because of the Crank-Nicholson equation. Let's take a look at that right-hand side of the equation one more time. We see at the first row and the last row, we had to tack on these extra r times temperatures. So let's do that here. So we'll say that the first temperature is going to equal the first temperature plus r times the temperature at 0. And then I'm just going to copy and paste this because it's a little easier. And instead of at 0, it's at -1, and the same thing with the temperature, -1. So shift enter, and let's look at, oh, you know what? That needs to be a B instead of a T. There we go. That would have been bad. So now if we look at B, these values changed a little bit, which is what we want to see. Okay. So now I think we're ready to actually go into, we're going to use the Salt Bandit. We should probably import that first off. So let's copy and paste this in, and shift enter. So now we can actually go in and say solve banded, and what does it want? Well, it wants the values for the number of lower and upper bands. And if we saw here, we just had one lower and one upper, so that's pretty easy to do. So 1 and 1, and then our value for A, and then our value for B. If we shift enter, we can see that it is slowly filling out our temperature profile. So what we want to do is we want to repeat this nt times, the number of steps we're taking in our time. So if we go for I in range 1 to nt, we will tab this over. Let's see here. There we go, and we'll set it equal to our temperatures from 1 to -1, just like so. And then, because our values for B depended on temperature, we want to copy and paste those back into the for loop, just like so. There we go. And then we probably want to add it to our figure as well. So we'll go if I modulo 1,000, and we can change that if need be, equals 0. We will add it to figure 2. So let's copy and paste this over, and instead of initial, we'll just call it I. And then at the very end, we want to show the figure 2. So fig2.show. Perfect. And let's see if this runs. Just thinking, yeah, there we go. Okay, I do want to show a little more lines. So we'll say something like 200. That'll add some more lines to our figure. And here we go. Perfect. So what we can see, just like we saw beforehand, our temperature profile eventually became a straight line in between the temperatures at the first and last parts of the bars. But this time, we already proved that there are no restrictions on our value for R with this Crank-Nicolson approach. So what we see here is our temperature profile without any restrictions, which is exactly what we wanted, and which is exactly what we were told to find.